So this one is lecture number 13, and here we will talk about methods of estimation, uh, and we will also talk about consistency of an estimator before this. So coming to outline of today's lecture, first we will talk about consistency. Till now we have already discussed about efficiency and sufficiency of an estimator. So I told that estimator happens to be a function of observations that you are observing in order to get a sample of fixed size n. So simply you can say that a estimator in a very specific kind of statistics. Okay, and we are up very much interested to know various properties of estimator. Then what are the characterization through which we can see the robustness of an estimator, that we had already discussed two of them, that efficiency and sufficiency. Today we will talk about whether once we come up with estimator, that estimator is consistent or not. What does it mean consistent? That means in long run whether it will give a very good estimation of the involved parameter or not, or parameter of interest or not. That means we will see asymptotic nature of the estimator. And after that I will talk about two important approach of performing estimation. That means estimation means parameter estimation simply in sense. So we will talk in detail how what are those approaches. One approach you know from linear algebra, that least square approximation. Nothing, just in linear algebra we are calling it a projection approach. That thing you had already seen that in linear algebra. Today we will see in different perspective that that would be also from approach would be from statistics. It would be statistical approach, or simply you can say that statistical model. And even I most of machine learning model, almost every machine learning model, I used to call it statistical model, because all those are coming from some kind of data. From there we introduce some kind of model structure, and after that we come up with the best model. So that's why you can call mostly statistical model. So coming to consistency of an estimator. So before that, we had already discussed about sufficiency. So and it is very difficult to come up with unique representation, unique sufficient statistics for a parameter. So what we do? So sometime uniqueness would be not there in case of sufficient statistics, and there might be more than one representation of estimator. For if something you come up with one sufficient statistics, there might be more than one representation. So what is happening, that in place of that unique sufficient statistics, we need to apply here minimal sufficient statistics. And what does it mean, say that? So for what is meaning of minimal uh, minimal sufficient statistics means it is that if you are having a statistics t of x, t as you are having, and how, when you can say that if you are coming with another statistics or estimator, better estimator, then what is happening, that estimator happens to be function of the current one that you had already taken. So in that sense you can say that this actually this generator or other all other statistics related with the particular parameter of the interest. So that's why this the generator of all other uh, or least estimator that generate others, so we are calling that as a minimal sufficient statistics. So that is the concept. And now we'll talk about consistency. So the estimator converges in probability to the population parameter being estimated when sample size is very large. That means when sample size n is going to approach infinity, then what will happen? What estimator you are getting, that will converge to the true parameter value of true parameter when n is approaching to infinity. So in that perspective we are calling it the theta n. It is a consistent estimator of theta. If it is not going to converge to theta in long run of the sample size, then simply we can say that that estimator is not consistent, and we should not proceed with that. So it is all these are part of law of large sample theory. You can say that. So when sample is happening to be very large size, so that time you will observe that you are trying to approach toward population. So, and if you are trying to approach toward population, what does it mean? So whatever is sample statistics you had, that one is also approaching towards your parameter. So that is the sense. That means if someone is willing to calculate mean of the population, it is not feasible. So what that person is going through a sampling approach, and in place of mean, that person is finding sample mean. And if that person is what that person is doing, he or she keep on increasing the sample size. So if that person is keep doing in that perspective, what will happen finally? That person will take a sample that would be very close to population, and hence what estimator you will get, that would be very close to the parameter. So that is the that is the perspective of convergence, that is the perspective of consistency of an estimator. So that means in long run, definitely that would converge to, if that estimator is going to converge to the parameter, then we can say that the corresponding estimator is an consistent estimator. So long run, we are talking about long run. For example, if you are taking sample mean x bar, this one is a sample mean. So sample mean, it is a consistent estimator of the true mean. True mean generally we denote it by mu. Remember with notation, various notation till now I had taken. So mu is meant for population mean, sigma square is mean for population variance, sigma is mean for population standard deviation, and if you come to sample, then x bar we denote sample mean, and sample variance we denote it by capital X square, and sample standard deviation we denote it by s. So these are coming with respect to sample. These are the sample statistics or estimator. You can simply say that estimator, and in right hand side you will observe the true parameter, and these are coming with respect to population. These are related with population. So complete, that means all, every individual is coming here, and hence we are calling these things, these letter mu, we all these are what Greek letter. So generally with Greek letter we denote population parameters. So these are parameters, and in left hand side, what are these? These are either you call it statistics, or you can call it estimator, because here your planning is that you want to estimate these parameters. So better name, local name, you can say that these are estimator. Or also you can say that statistics, that one is a general name, you can say that. So these are actually estimators only, you can say that. And remember that these are random variable. So these are coming from sample. So that is the difference. So we are talking about in consistency, we are talking about convergence of estimator to the true parameter. So and hence here we can see that this sample mean, it is a consistent estimator of mean, true mean, that population mean. So always you will see that if you increase the sample size, definitely it is going to converge to uh, mu, converge to mu. Okay, so now does unbiasedness imply consistency? And also we had seen one definition of unbiasedness. So this one is talking about convergence of sample estimator or estimator to true mean. But also we had seen one definition similar to that, unbiased estimator. Definition of unbiased estimator was what? Sample mean is an unbiased estimator. That means if you try to find mean of the corresponding estimator, then the mean would be equal to what? True parameter. That is the definition of consistent estimator. Or in general, if you want to write it like this way, then you can write it like this: capital theta cap, it is your estimator, and if you are finding mean of that or expectation of that, that one is equal to true parameter. So and hence we are calling it an unbiased parameter and estimator. Okay, so suppose here we are always here there is no need of that sample size should go to infinity, because it is directly equal to this one. So here can we say that is it equivalent that both definition unbiasedness and this consistent, because here it is talking about convergence of in short you can write it like that, I had already written. So it is talking about in long run our estimator is going to converge to the true parameter theta. This one is talking about convergence, but this one is talking about equality. That expectation of this one is equal to theta. In average, theta simply you can say that in average theta cap is equal to theta. Okay, so can we say that these two are equivalent to each other? Both are implied to each other? No, no, it is not. Not simply it is not true. How? So consider an observation xn, and just we take first observation x1. Okay, so definitely it is a what, uh, uh, if you are taking x1, can you say that it would be an unbiased estimator? How it would be an unbiased estimator of a mean? Anyone can comment over this? How, if you are taking first observation just x1 and you try to define a sample an estimator of the mean, that like sample mean, so can we say that sample mean due to the first observation only would be an unbiased estimator? Anyone can, when anyone may comment over it? How can you say that x1 would be an unbiased estimator of mu? Anyone? It is very simple that you are taking a sample of size 1, that means first observation. So what would be your sample mean? X bar would be just x1 divided by number of that sample size. How many sample size? Sample size you are taking 1. So x1 divided by 1, that means your sample mean is x1 itself. X1 itself, and we had already information that a sample, whenever you define sample mean, that sample mean is always an unbiased estimator. So you can say that that mean of bar, it would be equal to mean of x1, and that would be equal to true mean, that mu. So and hence if you are taking a single observer, a single observation, and with that if you define a sample mean, that would be definitely an unbiased estimator. Why? Because sample mean would be equal to that x1, that observation x1. So that is the, due to that I had to mention here x1 is an unbiased estimator of mean mu, true mean mu. So that is if it is unbiased estimator, then what would happen? Then mean of the x1, it would be equal to true mean. But now what we do, letting n tend to infinity, let it grow, sample size let it grow, then what does we say that x1 is going to converge to mu? No, it is not possible, because it is having single observation. We can't say that, n is not involved here, so we can't say anything. So despite of x1 is being an unbiased estimator of mu, x1 we can't say that it is a consistent estimator. We can't say that. So unbiased estimator is not implying consistent consistency simply. So that is that. So going further, other kind of consistency. One is, yes. Any question? Anyone is having any question? Because if you have any question, you ask. Otherwise, just mute your mic. Mute your mic if you don't have any question. Okay, fine. So we will talk about one other a specific consistency. That one is a square error consistency. So what is happening? That means we will define, yes. Yeah, expert definitely it is an unbiased estimator, because that one is a sample mean. Actually, x1, listen here, x1 is a first observation, x2 is second observation. So you are free to define a sample mean of any size. So suppose you are defining sample mean with sample single sample, single size. So that sampling process I had taken that in sampling you are taking only one member of the x. Okay, only one. So this one is a sample of size 1. Next time you can go define sample of size 2. So if you are taking sample of size 1, then x bar would be just equal to x1. That means here you did a sampling with just one sample only. If you are going for here two sample, then your x bar would be here x1 plus x2 divided by that sample size 2. Like you can go xn up to and you define in the similar fashion. Better you can put it here prefix, there is a suffix, you can put it here, or here xn you are dealing with them. So here you are just taking only one sample, and hence x bar is equal to x1. So and we have already seen that I had already discussed that x bar is a unbiased estimator. That means mean of x bar is equal to theta mu, that it is estimator of mean, so mu it would be not generally theta, and here x bar is equal to x1, so we can say that mean of x1 would be also equal to mu. That's way x1 is an unbiased estimator. Did you get it? Okay, you are free to take a sample of any size. It depends upon your choice. Because if you are taking a very good sample size, then your estimator would be very good. If you are taking very less sample size or something, it is not in your good condition, then your approximation would be not good. But the corresponding sample mean what you define, that would be always an unbiased estimator. So remember, the sample mean is always an unbiased estimator. It is defined like this way. Likewise, also I had told that this sample variance. So in the definition of sample variance, I had taken the here what is if generally if you define variance in population, how you define variance in the population, how you define variance. So you are taking, suppose n number of data you have taken, so take it like xk, k varies from 1 to n, xk minus you are taking also n number of data, that one is the population size. Suppose n is the population size, so we are getting mu as well, and we are trying to find variance. So how we find variance? We sum the square of mean deviation. We deviate all the data by mean and do a square. After that we divide that sum by sample, that number of not sample, population size, n is the population size. So then we are getting this quantity, we are calling it variance sigma square if n is the population size. But you remember that if we are dealing with sample, this one is a story of populations. Population, that means population is having n number of points. Suppose just you take sample and sample of size n, then situation is different. If you define sample variance like this way, then you will see that sample variance would be not a unbiased estimator. So intentionally we have to do one correction. We are taking correction that 1 by n minus 1 summation over mean deviation. That means xk minus, here we don't have true mean, population mean, so we are taking sample mean x bar square mean deviation, and sum from 1 to in n. So this one is what, here you can observe that 1 by n minus 1 is coming. So due to this factor we can say that this s square is an unbiased estimator. That means if you find the mean of this one, it would be equal to variance of the population, it would be equal to this kind of situation is coming. Okay, so all these are sample mean, what till now I have defined. Most of things are unbiased estimator, and most of things also would be consistent. If you are taking a sample size, if you keep on varying sample size, then that will be consistent. So this sequence here, sequence, it is sequence you are taking with respect to n. Remember that always you should focus on that word. You can ask one question, what is n? N is here sample size. Remember, this n is sample size. So if you're taking sample of various size, then you will get in that process you will get a sequence of estimator, and if that sequence of estimator is going to converge in a square error. So this mean square error in during efficiency, I had already defined mean, m for mean, s for a square, e for error. So how error we are getting? So error we are getting when we try to estimate the true parameter. So theta cap is the estimator, okay, and we try to see that definitely it would be not equal to theta exactly. So there is an error. This we are calling it estimation error. This is estimation error. After that we do a square. So it becomes a square error. Then we to take mean or expectation. Mean and expectation both are the same word. Then it becomes mean square error. This is the mean square error. So if you talk about convergency of an estimator with respect to this mean square error, then and if it is converging that when n tends to infinity, this mean square error it becomes 0. Then we say that this estimator theta n is converging to, it is consistent in mean square error, consistent in square error, mean square error, that is the. So various here norm loss function you can introduce, various that error function you can, error function, loss function, various things will come. So most of error function, loss function, those are coming with respect to norm, L1 norm, L2 norm, L3 norm, L4 norm. Likewise, depends upon your choice what kind of norm you want to proceed with. So generally people are taking L2 norm, that means a square norm, a square norm that I had already discussed. So and hence this we can represent in short like this way. This estimator theta n is converging to theta in mean square error. MS means mean for mean square error. So a square error consistency implies that both the bias and variance of an estimator approaches to zero. So you can I had already discussed about bifurcation of mean square error in the term of two part. So if you are taking mean square error, that can be bifurcated into two part. Variance of the estimator, one first component was the variance of the estimator. If you Google about machine learning, then bias and variance is a very common thing. And other part was what? Bias. Bias is what? That means when an estimator is not unbiased, then what would happen? Biasness will come. That means difference between mean of the estimator and true value of theta, this bias variance. So if you're this it I haven't mentioned here this one is an unbiased estimator, it is, I'm taking a sequence of estimators. So remember that if I had taken sample mean, then by default this bias would be 0 because it is unbiased estimator. So if I had taken this one, then there would be no such component. So it would be 0. Only variance, we would have only variance of the sample mean, and that variance is also equal to variance of the population mean. So that we would have that kind of thing due to unbiased uh, variance. So variance of that mean would be sigma square by n would be also there. So simply a square error consistency implies that both the bias and variance of an estimator approaches to 0 when n tends to infinity, because if we know that our mean square error is the sum of variance and bias of the corresponding estimator, and if in long run this one is approaching to 0 when n tends to infinity, then what will happen? We know that variance is always a positive quantity, and bias here we are taking a square of bias. If this term left hand term is approaching to 0 and n tends to infinity, by default the right hand term would be also 0. It would be 0, and we know that both quantity are greater than equal to 0. Least value possible value would be 0, and hence both must approach to 0, both must approach to 0, and hence we can say that this consistency of an estimator leads to our unbiasedness as well when in long run when n tends to infinity. Okay, so I am going further. I will talk about few notation from computational point of view. So these notation are very common. One is little o notation, another one is big O notation. So little o, what does it mean, meaning of little o notation? So a sequence action is said to be of order n to the power delta. That means order less than it, that action quantity it is less than less than n to the power delta if you multiply nth term of the sequence with n to the power minus delta. That means you do this ratio. You are defining xn divided by n to the power delta, and it is approaching to 0 as n tends to infinity. Then we say that n tends to infinity. Then we say that x xn is of order uh, little o of n to the power delta. So for example, if you take xn, you are taking a sequence of integer like this n to the power cube, n to the power 3, then you can say that if you divide n to the power 3 by n to the power 4, then what would be that would quantity would be 1 by n, and that would approach to 0, and hence we can say that a sequence n to the power 3 is what we call little o of n to the power 4, little o here, little o of n to the power 4. So that means delta, if xn is of order something, some power something, then you have to take in denominator you have to take little bit more than delta would be here in this case. If you take n to the power 3 plus delta, then definitely due to that delta contribution, that denominator it will be heavier, or that due to that heavier part, the ratio will approach to infinity when n tends to infinity. Another notation that we are calling it BIGO notation. So a sequence xn, we will say that it is of order BIGO of order n to the power delta. That means order at most then delta if is same thing we do, uh, we divide the nth term of the sequence with n to the power delta, and here we are not talking about conversion to 0. Suppose it is converging to any number, any constant as n tends to infinity, then we can say that the sequence is of big O of n to the power delta. So for example, you can take it this function. If you are taking this function, and you what you do, if you divide this with x to the power 4, then what will happen? So this term will be constant, it will approach to 6, and this term would be what? It will approach to 0 when x tends to infinity, it will approach to 0. This will be approached, also this will approach to 0. So you can say that this function f of x, I should write it, it is function f of x. F of x is of order big O of order 4. Big O of order 4. You can say like this way. That means, and if you talk about same thing with from the little o perspective, then if you divide with x to the power 4, then it is not, this term is, this expression is not going to approach to infinity, no 0, it won't approach to 0. So in order to make this 0, what we have to do, we have to divide with x to the power 4 plus something positive, then due to this something positive will lead toward this quantity to 0 when x tends to infinity. So this quantity is of order x to the power 4 plus delta in little o notation, but x to the power 4 in big O notation. So these are the little o and big O notation. These are very much essential in computational perspective, and when we will talk about various algorithms, that time you will come to know. I will talk about in model 3 optimization algorithm. So definitely there, that bound would be of order something, what order it would be, I will talk. So a special case that if you are getting big O of 1, that means it is simply talking about constant, nothing. Okay, it is talking about constant, that what I had discussed. So the order of variance gives the order of sequence of random variables or observation. So we need to see that what is the order of variance, what is the order of mean. Now variance generally we know that sample mean is an unbiased estimator, we know that. But if you try to find the variance of this one, the variance of sample mean is sigma square by n. So what we observe here, it is of order big O. So that means big O of order 1 by n. That means if you divide this by 1 by n, then this quantity will converge to some constant. So we can say that variance of sample mean, that means sample, that estimator of mean, it is of order 1 by n. Similarly, so let again here it is cap. So theta cap of an unbiased estimator of any parameter theta, then we have to see that how fast does this theta cap converge to parameter theta. So that means we have to see the rate of convergency. So rate of convergency always need understanding of little or big O notation. So the sample mean x has its variance. We know that variance I have already defined. You can calculate it. Variance is sigma square. Very simple. If you easily you can calculate sample variance of sample mean, that would be sigma square by n, and it is of order 1 by n. That is the convergence is at the rate of if you talk about convergence is in the rate of n to the power 0.5 negative 0.5. Why? Because it is variance. Variance is talking about a square. So in order to find what convergence, you have to mean is what it is uh, it is mean. Simple mean, if you take variance is defined with a square thing. Mean is uh, simple it is defined with order of random variable, but variance is defined with order of a square kind of thing. So in order to talk about convergency, you have to take a square root of the variance in order to make in the same unit. But that means unit of, if you take unit wise unit, then mean and sample mean and the variable would have same mean, but variance would have a square unit. So that's why you have to bring in the same. So if you take a square root, then a square root, that means you are defining sample variance. Sample deviation would be sigma by a square root of n. You have to talk about. So that's why if you talk about this one, so this one is will converge with this rate. This rate, this we are calling it root and consistency. So let uh, this theta cap, it is a consistent estimator of theta, and same thing I have described here. So it is same thing coming here. So an estimator has variance of this order, BIGO of 1 by n to the power delta, twice of delta, and we see, from that perspective we say that estimator is n to the power minus delta time convergent, root n convergent. And suppose that variance is if suppose variance happens to be 1 by n square of BIGO, then we will say that it is xn would be what it would converge, and it would have n convergency, because a square of what this one, it would be what a square of this one would be n. So that's why n convergency. So the usual convergence is root n. If an estimator has a fast convergence, then we call it super consistent, then higher degree of convergence. That n to the power minus n to the power n to the power minus 2 minus 3, as much as you know that if you talk about convergency of this one, this convergency of sequence 1 by n is slower than convergency of sequence 1 by n square. Rate of convergency of this one is much faster, and rate of convergency of nq is faster than these two. So likewise, if you keep on increasing the power, then convergency rate will keep on growing. In the denominator, if you keep on increasing, convergency rate will keep on growing. Now further I will talk about method of estimation. So there are various method of estimation. So there are two philosophy in order to estimate an parameter. So one philosophy is leading toward parametric, another philosophy leading towards non-parametric. That means in parametric we are giving a model, proper model or structure to the problem. That model, that means whether it is linear, non-linear, we are giving proper model or structure. That means we are introducing parameter, and we try to estimate that parameter. That one philosophy. Another philosophy, we are not approaching parameter directly, we are estimating the function. Suppose someone is saying that we are having data and those data came from some distribution. That means some distribution, it would be p of x, but we don't, or simply call it f of x, but we don't know the distribution. We don't know the distribution. So there are two approaches to estimate the distributor. One approach that you can parameterize the distribution. That means you introduce one parameter. If you parameterize, then you convert this one directly like this way. You introduce parameter theta. So you are giving a introducing a parameter, and you are giving a modular structure. That means it is defined like something, x and theta as a function of x and theta, and then theta, after optimization, or we try to estimate it in order to get this function, okay, this density function. Another approach is that we want introduce theta directly. We try to estimate f directly without parameterizing. We try to estimate this one. So that approach we are calling it non-parametric, and this part is a little bit difficult, but this one looks easier. So in parametric approach, it assumes data come from a type of some probability distribution and makes inferences about the parameter of the distribution. That means there parameter is coming explicitly there, and we try to estimate that parameter. So model are parameterized before collecting the data. Like example is least square estimation or maximum likelihood estimation. All these are what parametric approach. And in non-parametric approach, it assumes no probability distribution. That means they are distribution free. Model are not imposed a priori but determined by the data. So that means one kind of those approaches we are calling it histogram, kernel density estimation, all those. So these are little bit difficult problem. I won't discuss this in model 3. I will discuss just first approach, parametric approach. So first parametric approach, that one is least square approach. So what we do here, so there is a functional form for if you try to estimate with y, we try to estimate y as a function of x, but we don't know the actual formula of this one. So what we do, we will take a functional form of y which involves theta. This function depends on non theta, and the relation between y and x. X is what your input variable. You can simply say that there are p number of input variable, and y is the response or output variable. Simply you can say that, and we don't know how y depends upon x through which function. We don't know. So we have to understand that. So what will happen if you do in that sense? There is an error that we denote it by epsilon, and we will estimate the parameter theta by minimizing a square of the error. So that's why this approach we are calling it least square. That means we are trying minimizing. We try to find the least value of the square error. So this approach we are calling it mean square error or least square estimation. So what is the functional form? So we parameterize the hypothesis function f of x. That means we try to express this y as a function of x, but we don't know that function. So suppose there is a known function f. So y would be function of x, y equal to f of x, but we don't know f. So in order to estimate f, we parameterize it. We introduce parameter theta. So that we f of x we are writing as function of x and theta, f of x theta, and hence we give here this form. So this, so yi for each sample, I is talking about m number of sample we have taken. So yi equal to f of xi theta plus this error term. This is the error term we are calling it. Okay. So typical assumption that we take that here f of x theta is correctly specified. That means we need to know a particular model structure, how it would be defined. Simplest one is that it is well defined. It must be well defined. Simplest one is the linear model. So that what we do, f of x theta we define it as some data matrix times theta. So theta, this x we are calling it sometimes full rank matrix, sometimes it may not be full rank matrix. So various assumption we can put it, whether it is a full rank matrix, that this bold x, it is talking about what data matrix that in very first class I had discussed. So you can put further condition over this data matrix, and further one more, that means this X is a full rank matrix. That one is equivalent to saying that if you try to find conditional what conditional expectation of error with respect to this data matrix, that means X is your given, it is just constructed from the given data, that given data X, so that's why it is in your hand. Okay, so if you observe that the conditional expectation of error with respect to this one is 0, then simply we say that a error is what perpendicular to X from the linear algebra perspective, or error is what identically distributed and independent Gaussian distribution. Also it is coming from, just for better understanding, I'm saying that it is coming from Gaussian distribution. So other thing I will discuss in next class. In regarding attendance, just put your roll number there in the comment box, and if you are having any question you can ask.